Okay, so we're going to begin our kinetics unit, and kinetics is specifically concerned about the rate at which a reaction occurs. Now in the last unit, thermodynamics, we weren't concerned about how fast a reaction occurred, we were concerned about whether a reaction would occur or not. A reaction that would occur is called a spontaneous reaction. And a spontaneous reaction, if you remember, is a reaction that will occur given enough time. So in thermodynamics, we didn't really worry about whether that unit of time was a fraction of a second or 1,000 years. All we were worried about was, will this reaction occur? So now we'll look at reactions that are spontaneous and how long does it take those reactions to occur. So in this unit, we'll look at these different things that affect the rate of reaction. We're going to spend some time the first couple days looking at concentration and how that affects reaction rate, and then we'll continue on and look on a molecular level at what's happening with rate and talk about some of these other things that happen as I speed up or slow down the reaction. So, meaning of rate. Remember, rate is change over time. So when we're looking at the rate of reaction, we can look at how fast are products being produced, which is often called the rate of appearance of products. Or we can look at how fast are reactants being used up, which is often referred to as the rate of disappearance of a reactant. In either case, whenever we're looking at rates, the way we measure the rate of a reaction is the change in molarity over time. So the units are moles per liter per whatever unit time I'm concerned with, seconds, minutes, days, hours, whatever. And remember, moles per liter is molarity, so I can just write that like this. Okay. So let's look at this reaction up here. Hydrogen peroxide decomposing to form water and oxygen gas. So when I look at the rate of disappearance of H2O2 and the rate of appearance of the products, I notice that the rate of disappearance of H2O2 is the same as the rate of appearance of H2O. You'll notice that 2 units of H2O2 were used up and 2 units of water were produced. And that's based on the stoichiometry of the reaction. That tells me either 2 molecules of hydrogen peroxide produce 2 molecules of water, or 2 moles of hydrogen peroxide produce 2 moles of water. Likewise, as 2 of these get used up, only 1 oxygen molecule gets produced. So again, looking at the stoichiometry, I notice there's a 2-to-1 ratio. 2 moles of H2O2 will only produce 1 mole of oxygen gas. So that's kind of a qualitative look, or a semi-quantitative look at what's happening. But if we were actually to put a number to the rate, so how fast is H2O2 being used up? It's being used up at the rate of 4.6 moles per liter per minute. If I have a 1-to-1 mole ratio for H2O2 and H2O, that tells me that water will be formed at the same rate that hydrogen peroxide is used up, because they're formed at a 1-to-1 ratio. It also tells me that the rate of formation of O2 is half as fast as the rate of disappearance, or rate of consumption, of hydrogen peroxide, because for every 2 hydrogen peroxides I only get 1 water. So I take that rate and divide, 1 oxygen, excuse me, not 1 water. So the rate of production of O2 is half the rate of disappearance of hydrogen peroxide. If I were to graph these things, graph the disappearance of H2O2 and the appearance of oxygen over time, I would get these 2 curves. You'll notice we can tell immediately by looking at this curve that hydrogen peroxide is a reactant because its concentration goes down over time. Likewise, I can tell that oxygen is a product because its concentration goes up over time. And in a minute we'll talk a little bit more about the shapes of these curves and what that means. But for right now, just realize that by looking at a graph you can tell whether you're talking about reactants or products just by looking at which direction concentration is changing. Okay, so here's an example problem. I have nitrogen and hydrogen forming ammonia. So if nitrogen disappears at the rate of 0.1 mole per liter per minute, what is the rate of disappearance of H2, the other reactant? What's the rate of appearance of ammonia, the product? So when I look at the mole ratios, I notice that 1 mole of N2 requires 3 moles of H2. So for every 1 mole of N2, I also use up 3 moles of H2. So the rate of disappearance of H2 is 3 times the rate of disappearance of N2. So if I'm chugging along at 0.1 moles per liter per minute, if I multiply that by 3, that tells me that the rate of disappearance of H2 is 0.3 moles per liter per minute. Because of that 3-to-1 ratio. Likewise, if I'm looking at ammonia, 1 mole of nitrogen produces 2 moles of ammonia. So, for every 1 mole of nitrogen, I get twice as much ammonia. So, if I'm going along at a rate of 0.1 mole per liter per minute, if I multiply that by 2, that tells me I get 0.2 moles per liter per minute, and that is the rate of appearance of ammonia. So let's go back and take a little more qualitative look at the graph of just looking at the change in concentration of hydrogen peroxide over time. So this is similar to the graph we looked at before, except it just has hydrogen peroxide, and here is that graph with some numbers attached to it. So it's more quantitative than that last graph we looked at. So there are actually several different ways we can look at how fast is this reaction occurring. One way I can look at it is to look at the average rate from time 0 to, in this case, time 600. Over this whole course of time, you'll notice that this is a curve. This is not a straight line. So the rate is not constant. But if I'm just concerned with just about, well, how long is it going to take, I can talk about the average rate over this whole period of time from 0 to 600. If I find the slope of that line, that will tell me the average rate over the whole 600-second period. Another way I can look at this is to look at the rate at a particular moment in time. So if I want to know how fast is the reaction going at exactly 300 seconds, I would draw a line tangent to the curve at 300 seconds. The slope of this line would be the instantaneous rate, and that would be the rate at only 300 seconds. The third way to look at this is to look at something called initial rate. And an initial rate, you can see at the top, if we just look at the top little few seconds of what's happening here, the rate of change is almost linear. So if we just make that linear from the beginning, we get this other line, and the slope of that line is called the initial rate. And as it turns out, the initial rate is the one that's easiest to measure in the lab, so that's the one we tend to use in chemistry lab.